Today, we are looking up, way up. We're diving into a risk that honestly feels like it's lifted straight out of a sci-fi movie.
It really does.
We're talking about what happens when our own star, the sun, decides to fire off what is essentially a plasma bomb, straight at Earth.
And how that one single event threatens to, completely dismantle the 21st century infrastructure that we all rely on for everything.
Exactly. We're exploring the risk posed by what scientists call solar superstorms.
It's a classic low probability, high impact scenario. And, our sources make it really clear that the stability of modern civilization is resting precariously on the behavior of a star that's 150 million kilometers away.
And the sources paint a genuinely staggering picture. I think the central paradox we're exploring today is this. We're facing a catastrophic event, something that could cause global blackouts lasting not just for days, but potentially for years. And yet, the key to surviving this, our best defense for our massive interconnected electric grid, might actually lie in something surprisingly mundane.
Right. Simple electrical components. We're talking about things like capacitors or similar technologies that just block current.
That's the conflict, isn't it? This huge astronomical threat versus this surprisingly simple engineering defense.
That's the essential question. Why are these humble components, these devices, designed to just block stray DC current? Why are they our best firewall against our own star?
So let's set the stakes, because they are staggering and they directly affect you, the listener. We are talking about a repeat of an event from 1859, the Carrington Event, happening today.
And the analysis from places like the Department of Homeland Security warns that a storm of that scale, it could lead to economic losses estimated, and this is conservative, at $2 trillion.
In the first year alone.
In the first year. And potentially affecting power for hundreds of millions of people.
And like you said, the real catastrophe isn't the initial flash, it's not a temporary blackout. The problem is how long it takes to recover.
That's the core issue. A strong solar storm could physically burn out critical high-voltage components, specifically these gigantic custom-built transformers.
Large power transformers, or LPTs.
Exactly. And that leads to the doomsday scenario. Blackouts lasting months or even years, simply because we cannot replace that hardware quickly.
Months to years without electricity. That's
right.
That's the definition of a civilization crippling event. Okay, let's unpack this. Let's start with some definitions so we're all on the same page. The source of the trouble is something called a coronal mass ejection, a CME.
Right. CMEs are the headline act. They're these massive explosions of superheated plasma, so highly charged electrons and protons, and the magnetic fields that are tangled up inside them.
And they get released from the sun's corona, its outer atmosphere.
You can almost picture it as the sun just ejecting this gigantic, highly magnetized bubble of gas into the solar system. Billions of tons of matter.
It's just hard to get your head around that distance, 150 million kilometers.
Yeah.
So once that eruption happens, how long do we actually have before it gets here?
Well, the good news is they're slow compared to the speed of light. They're fast, but not that fast. So they typically take between 1 and 3 days to reach Earth.
Okay, so there's some warning.
There is. That transit time gives us a crucial, albeit very narrow, window. Sometimes as little as 16 to 18 hours in the worst case. That's the time grid operators have to react.
That small window is everything. And the result of that magnetic cloud hitting us, the thing that actually does the damage on the ground, that's called a geomagnetically induced current, or a GIC.
Exactly. And that's the mechanism we really need to understand. That's the fundamental physics of failure.
Okay, so now that we've got the source, the CME, and the result, the GIC, let's move into part one. Dissecting this solar activity and understanding precisely why the sun's violence turns into a broken transformer here on Earth.
And a crucial starting point is making the distinction between the two primary solar threats, because people often use the terms interchangeably.
You mean solar flares and CMEs?
Right. They affect our planet in very, very different ways.
Okay, let's start with the faster one. Solar flares.
Solar flares are intense bursts of electromagnetic radiation. Think X-rays and gamma rays. They travel at the speed of light.
So they get here in just 8 minutes.
8 minutes. So basically no warning.
And the damage they cause.
It's immediate, but it's short-lived. Flares primarily mess with the upper atmosphere. They ionize it, which causes these wide-area blackouts of high-frequency radio communications.
So radio blackouts. Ham radio operators, pilots, they'd notice this immediately.
They would, but they don't cause physical damage to the power grid itself. They're a communication problem, not an infrastructure one.
So the radio blackout is the first sign, but the real ground-based threat The one that causes the permanent physical damage that comes from the slower, heavier punch of the CME.
Precisely. The CME is what drives the long-duration geomagnetic storm. When that massive magnetic cloud finally arrives, that's when it dumps enormous energy into our magnetosphere and drives those damaging currents on the ground.
And how often are we talking here?
Well, it depends on the solar cycle. Near a solar maximum, the sun can produce about 3 CMEs every single day.
Wow.
But, only a tiny fraction are actually aimed at Earth. Near solar minimum, that drops way down to maybe 1 CME every 5 days or so.
Okay, so let's connect the physics. This is where I think a lot of people get lost. How does a cloud of magnetized plasma, 150 million kilometers away, generate a damaging electrical current in a transformer bolted to a concrete slab in, say, Ohio?
It all comes down to Faraday's law of induction. It's pure electromagnetic physics.
Right, yeah.
So when the CME's charged particles in its magnetic field slam into Earth's protective magnetic shield, our magnetosphere, they cause these rapid, violent fluctuations in our planet's own magnetic field.
And a changing magnetic field induces an electric field. That's the core principle.
Exactly. The bigger the change, the bigger the field. And these fluctuations generate a surface electric field right here on the ground.
And normally that field is tiny, right?
Negligible. On a quiet day, it's maybe around 0.1 volts per kilometer. But during a severe storm, like the Halloween storms in 2003, or a Carrington-level event, that can shoot up dramatically to 5, maybe even 10 volts per kilometer.
That's an increase of 50 to 100 times.
It is.
Yeah.
And that surface electric field is the engine. It's what drives the geomagnetically induced currents, the GICs. And that current then looks for the easiest path to travel through.
The path of least resistance.
Right, which happens to be our long, grounded, highly conductive systems, power grids, pipelines, old telephone lines, with the Earth itself completing the circuit.
This brings up a really crucial point you mentioned, geographical inequality of risk. It's not the same everywhere. The rocks under your feet actually matter.
They matter enormously. You can have 2 identical power stations, same latitude, but one is at far greater risk just because of the geology beneath it.
How does that work?
Well, the GICs want to flow. If the ground underneath is highly conductive, say it's sedimentary rock or wet soil, the current just flows harmlessly through the Earth. But if the underlying geology is highly resistive, like the huge ancient granite shields under parts of Canada, Scandinavia, the northern U.S.,
Then the rock basically says no.
the rock blocks it. So the current is shunted away from the Earth, and it finds the next best conductor it can, which is our infrastructure, the power lines, the pipelines.
So places like Quebec, which we're about to talk about, are just inherently more vulnerable because of 3-billion-year-old geology.
That's the key insight. The vulnerability was baked in billions of years ago.
That's incredible. It brings us perfectly into part 2, the lessons from history and this worrying trend that the more advanced we get, the more vulnerable we become.
And we have had warnings. The benchmark for all of this is still the Carrington Event, September 1st and 2nd, 1859, the most intense geomagnetic storm in recorded history.
I think we need to just pause and absorb the sheer spectacle of this. It sounds like something from a myth.
It was visceral. The auroras were so strong they were seen globally, in places they'd never been seen before. South Central Mexico, Cuba, Hawaii.
Even near the equator in Colombia. Imagine stepping outside in Havana and seeing the sky lit up in greens and reds.
I mean, there's that famous anecdote about the gold miners in the Rocky Mountains. They woke up in the middle of the night, thought the sun had risen early, and started making breakfast.
By the light of the aurora.
By the light of the aurora. People in the Northeast U.S. could read newspapers by its light.
But the real lesson for us today came from its impact on the most advanced technology of the time.
The telegraph network.
Right.
Even that simple system was crippled. The GICs caused severe damage all across Europe and North America. Telegraph pylons were literally throwing sparks. Operators were getting electric shocks.
And the most incredible detail is that some of them could actually disconnect their power supplies.
And keep sending messages. They were running their telegraphs purely on the GIC flowing through the wires. The Earth itself became the battery for about 12 hours.
A terrifying demonstration of GIC power. Now let's fast forward to the modern era. We get a second, much more sobering warning. The 1989 Hydro-Quebec collapse.
This was the modern wake-up call. And what's crucial here is that this storm, in March 1989, was only moderate compared to Carrington.
But it hit Quebec, which is on top of one of those geologically vulnerable rock shields we were talking about.
Exactly. So the grid there was highly susceptible. The storm hit on March 13th, the GICs flowed into the transmission system, and that DC current distorted the magnetic field inside their transformers.
And what does that do?
It causes them to consume a huge amount of something called reactive power, which is what's needed to keep the voltage stable. This sudden demand for reactive power just collapsed the voltage across the entire grid.
And the safety systems, seeing this huge problem, did what they were designed to do.
They tricked. The protective relays saw a major system fault and started shutting down huge sections of the grid to protect the expensive equipment.
It cascaded.
Incredibly fast, leading to a province-wide blackout for over 6 million people that lasted for 9 hours. And this time, there was real physical damage to transformers, not just in Quebec, but in the UK as well.
This really highlights that technological sensitivity trend. In 1859, the strongest storm we know of cripples simple telegraphs. In 1989, a moderate storm takes down a huge modern power grid.
Our vulnerability has scaled up disproportionately. The modern grid is bigger, the transmission lines are longer, which makes them better antennas for GICs, and the controls are much more sensitive.
So we're just inherently more susceptible.
Absolutely. Experts estimate that if the 1921 storm, which was about 10 times stronger than the 1989 one, happened today, it could leave around 130 million people without power in the U.S. alone.
That's staggering. And we tend to think of Carrington as the absolute worst-case scenario, but the historical data suggests the sun can do much, much more.
Right. We can look at proxies like carbon-14 isotopes trapped in ancient tree rings, and they suggest these massive radiation events happen in 774, 775 CE, and again in 993, 994 CE.
And how does that 774 CE event stack up against Carrington?
The estimates suggest the energy release was maybe 20 times greater than Carrington. Now, there's a big caveat. We don't know if the CME actually hit Earth or just missed us. But it forces us to consider a worst case that's even worse than Carrington.
So, history shows the threat is real, the vulnerability is increasing, and the potential severity is astronomical. Let's move into part 3 and get into the nuts and bolts of where our modern world is most fragile.
The modern threat is defined by these deeply integrated failure points. And the power grid is, without a doubt, the most critical vulnerability. We have to understand exactly why those large power transformers fail.
Let's start there. The grid's single point of failure, the LPTs. These are the giant, unsung workhorses of our energy system.
They are. They're massive, custom-built, highly specialized. And the GICs flowing through the power lines, they seek a ground connection, and they find it in the grounded neutral wires of these transformers.
So you have a pure DC current, the GIC, forcing its way into a component designed exclusively for an AC or alternating current system. What happens inside the transformer core when that DC hits?
This is the key mechanism. It's called magnetic half-cycle saturation. The core is made of steel that's designed to handle a symmetrical, alternating magnetic field from the AC current.
Okay.
But the GIC is basically a DC bias. It shoves the magnetic operating point of the core way off center.
Like pushing a spring too far in one direction so it can't bounce back properly.
That's a great analogy. The GIC pushes the magnetic flux into saturation during one half of the AC cycle. The iron core literally becomes magnetically saturated. It can't handle any more magnetic field.
And the physical consequences of that saturation.
Two big things. First, the transformer starts generating enormous amounts of heat from eddy currents and magnetic flux leaking out of the core. That causes thermal damage, it cooks the insulation, it degrades the windings.
And sex.
Second, it starts drawing huge amounts of reactive power from the grid, which, as we saw in Quebec, is what you need to maintain stable voltage. If enough LPTs do this at once, the whole system's voltage collapses. Widespread blackouts.
And here we are at the core crisis.
Yeah.
The logistical nightmare, the physical, permanent destruction of these LPTs.
This is the bottleneck. This is what turns a temporary solar storm into a multi-year disaster. LPTs are not off-the-shelf items. They are custom-built. They weigh hundreds of tons.
And the supply chain for them is limited.
Very limited. It's concentrated in just a few countries, and the current lead time to manufacture a replacement LPT is 2 to 4 years.
So if a Carrington storm takes out, say, 300 of these across North America,
we face a replacement schedule that spans a decade or more. That physical damage, plus that incredibly slow replacement time, is the root cause of the multi-year blackout scenario.
Okay, so if the power grid is the circulatory system, our next big vulnerability, positioning, navigation, and timing, or PNT, is the nervous system. Our reliance on satellites, especially GPS.
Right. The threat to satellites is twofold. There's direct damage, and then there's signal degradation.
Let's start with the damage.
Satellites, especially the ones in high orbits, are very exposed to solar energetic particles, or SEPs. This constant bombardment of particles causes cumulative radiation damage, which ages them rapidly. And more importantly, it causes single event effects, Cs.
Which is when a single high-energy particle hits a microchip.
Exactly. It can cause a soft error, like flipping a bit in memory, which can be corrected, or it can cause a hard permanent error, physically burning out a circuit and killing the satellite.
And the sources suggest up to 10% of the entire satellite fleet could experience temporary outages.
That's a conservative estimate, and the surviving satellites would age much faster, forcing operators to replace them years ahead of schedule. It's a massive expense.
And then there's the effect on the signal itself. Ionospheric scintillation. We've heard it's like stars twinkling, but what's actually happening to the GPS signal?
The energy from the storm creates these rapid irregularities in the electron density of the ionosphere. This doesn't just make the signal twinkle, it causes rapid random phase shifts, and it weakens the signal's amplitude.
So what does that mean for my phone's GPS?
It means the receiver in your phone or in a high-precision server for a bank, it can't lock onto the signal. The signal might be there, but it's scrambled and unusable. So for 1 to 3 days, GPS could be partially or completely inoperable.
And as you said, GPS isn't just for maps. It's the timing signal that runs the modern world.
It's the silent engine. Financial transactions, network synchronization for cell towers and energy grids, it all relies on that GPS timing signal. Losing it would trigger widespread economic gridlock.
Okay, let's turn to the internet itself, the subsea cables that connect continents. There's a lot of talk about an internet apocalypse. What's the real risk here?
This is where we need to separate the myth from the reality. The good news is that the cables themselves are fiber optic. They transmit light, and light is immune to GICs.
So it's not like the old copper telegraphs.
Right. But those cables aren't just passive pipes. They have to power optical amplifiers or repeaters every so often along the ocean floor.
Yeah, they power them with copper wires.
Exactly. There are long copper conductors inside the cable, and these power systems are grounded at both ends. They operate at very high voltages, like 10,000 volts.
So even though the data is safe, the power system that keeps the data flowing is still a giant metal conductor that's vulnerable to GICs.
It is susceptible, yes. But there's critical mitigation built in. Companies like Google have studied this. They tracked voltage fluctuations in their cables during smaller solar events and confirmed they correlate with the storm's strength.
And what did they conclude? Why are these cables safer than the power grid's transformers?
The consensus is that the risk of large-scale cable damage is pretty low, for 2 reasons. First, the power system is a DC system to begin with, so it's designed to handle that. And second, the grounding strategies are different from the massive grounded neutrals on the big utility transformers. The LPTs are just a much more appealing target for the induced DC current.
So there would be voltage spikes, operational headaches, but the internet's backbone probably wouldn't physically burn out.
That's the crucial distinction. The design of a 10,000-kilometer cable makes it inherently more resilient to this specific threat than an AC utility transformer is.
And we should just briefly touch on the other linear systems. Pipelines, railways.
Anything long and metal is a target. GICs in pipelines accelerate corrosion, which shortens their lifespan. And in railroad tracks, they can interfere with the signaling and control systems, which is a major safety concern.
Okay. So we've established a very clear, quantifiable threat. GICs hitting transformers and destroying them faster than we can replace them. Let's move to part 4. The hope, prediction, preparation, and these critical blocking technologies.
And we have to start by acknowledging the big limitation. We can't stop the storm. We can only prepare. And that preparation relies on forecasting, which is intense and still a pretty immature science.
And that warning window, again, is 16 to 18 hours, best case.
Best case. And that's just for the main magnetic cloud. The really high-energy particles from the initial flare, they arrive in minutes. We have basically no warning for those.
So why is space weather forecasting considered to be about 50 years behind terrestrial weather forecasting?
A few reasons. First, we just don't have enough data. We don't have a dense network of sensors out there like we have weather balloons and stations all over Earth. And second, the physics is just way more complex. We're not modeling air and water. We're modeling highly turbulent, magnetized, collisionless plasma.
And getting that modeling right is critical for the grid operators.
It's everything for them. They're mandated to take preemptive action when a G3 or greater warning is issued. But those actions are very costly. They have to reduce power flow, bring on extra reserves, maybe even take critical equipment offline.
So if the forecast is wrong.
Exactly. If they act on a false alarm, they lose millions of dollars and destabilize the grid. If they hesitate because they don't trust the forecast, they risk catastrophic failure. So they're in an impossible position.
And before we get to the fix, let's talk probability. I've heard people say we're overdue for a Carrington event.
That phrase doesn't really apply to random events like this, but a recent study put the chance of a Carrington-level event happening at about 12% per decade.
So a recurrence interval of around 79 years.
Roughly, yeah. So we're not overdue, but it is a current, actionable, and inevitable risk. The probability is high enough that we need to be taking it very seriously.
So if the forecast window is tight and the risk is inevitable, the best defense has to be engineering. Hard mitigation. Which brings us back to our central theme, just blocking the current.
That's the core strategy. You have to stop the GIC from ever getting into the transformer in the first place.
And how do we do that? We hear about two technologies, series capacitors and neutral blocking devices.
They're related, but they have different primary purposes. Series capacitors are mainly put on long transmission lines to improve overall grid performance and efficiency. A very useful side effect is that they happen to block DC current, like GICs.
So they're multi-purpose. What about the neutral blocking device, the NBD?
The NBD is the star of the show here. It is engineered for one purpose and one purpose only: GIC mitigation. You install it right at the transformer's neutral point, and it acts as a filter. It just blocks the DC from getting in.
And the sources suggest that doing this solves two problems at once, the catastrophic one and a chronic one that's costing us billions every year.
This is a really powerful insight. That chronic problem is the estimated $10 billion in annual economic losses caused by all the small, frequent geomagnetic disturbances.
So it's not just the big storms.
Not at all. Even small GICs flowing through transformers day after day, year after year, cause excess heating, vibration, and they break down the insulating oil. It's death by 1,000 cuts. It leads to premature transformer failure and higher maintenance costs.
So installing these NDBDs in high-risk areas not only prevents the Carrington-level catastrophe,
but it simultaneously eliminates that chronic degradation. It could recover that $10 billion in annual losses from increased maintenance and efficiency losses.
Okay, let's just step back here. This is the big question. If the technology exists, it's proven, and it literally pays for itself by reducing wear and tear. Why isn't it being mandated everywhere right now? What's the barrier?
That is the fundamental policy hurdle. The barrier is a mix of regulation and investment reluctance. Utilities see the upfront cost, and it's hard for them to get that approved in their rates for a threat that feels rare and distant to regulators.
Oh, it's that classic problem. Spending a lot of money today to prevent a disaster that might not happen for 50 years, even if that disaster is civilizational collapse.
That's the conflict. And in places like the U.S., the grid is so fragmented, getting dozens of different utility companies to all agree on a costly infrastructure upgrade is a huge political and logistical challenge.
So the conversation needs to shift from, can we fix this,
Yeah.
to when will we mandate the fix?
Exactly.
And even if we do that, we still need a backup plan. We need to address that LPT replacement bottleneck.
Right. We still have to plan for a worst-case scenario. That means we need a stockpile, a national reserve.
The Strategic Transformer Reserve, or STR. How would that work?
It would need to be a government-funded, coordinated national effort. You'd buy a number of these custom universal fit spare transformers and store them in secure, climate-controlled warehouses placed strategically around the country.
And the impact of that.
It means you bypass the 2 to 4 year manufacturing delay. A storm hits, you lose some transformers, you can ship out the spares and get them installed within months, not years. It preserves societal function. The investment is high, maybe $100 million, but compared to a $2 trillion disaster,
The cost benefit is obvious.
overwhelmingly positive.
Finally, let's talk about keeping the digital economy running if we lose GPS. We need resilient alternatives for position, navigation, and timing.
Given how dependent we are, resilient P&T has to be a top priority, especially for finance and communications.
And what are the main alternatives?
Well, one mature option is LRN, Enhanced Long-Range Navigation. It's a ground-based, low-frequency radio system. Because the signal travels along the Earth's surface, it's not affected by that ionospheric disruption that kills GPS.
Okay, so that's a good backup. What about the really high-tech, next-generation stuff?
That would be magnetic navigation, or MagNav. This is a system that uses incredibly sensitive quantum sensors to navigate by detecting tiny changes in the Earth's own ambient magnetic field.
So instead of looking up at satellites, it's looking down and using the Earth's magnetic signature as a map.
Exactly. It uses advanced AI to correlate its readings with a known magnetic map of the Earth. And crucially, it's totally immune to the ionospheric effects that disrupt GPS, and it can't be jammed or spoofed in the same way.
This has been an incredible deep dive into a genuine existential risk, but one that seems solvable.
It is. I think what this all means for the listener is that the sun poses a definite quantifiable threat, but the threat isn't really the physics of the storm itself. We understand that part.
The real danger is logistical. Our ability to recover, specifically that 2 to 4 year replacement time for large power transformers, is just completely insufficient.
We've built a system that's too brittle for the known forces of nature. And critically, the technological fix, these neutral blocking devices, is available, it's proven, and it's even cost-effective when you factor in the chronic damage it prevents.
So the risk, at the end of the day, is a question of policy and priorities, not technological impossibility. We know the danger, we know the defense.
And the choice is whether we invest in resilience now or face a potential multi-year collapse later, a choice that gets more urgent as we head towards the peak of the solar cycle.
And as we close out, I want to leave you with one final thought, one that kind of turns this whole conversation on its head. It's this idea that the sun is both our greatest local threat and our cosmic protector.
The great paradox, yes.
Despite all this focus on its destructive power, the star that threatens our grid might actually be protecting us from something even deadlier.
That's its function against galactic cosmic rays, or GCRs. These are extremely high-energy particles from distant supernovae from way outside our solar system, and they are very bad for human biology.
And the sun's magnetic field acts as a shield against them.
It does. It modulates the incoming GCRs. And counterintuitively, the flux of these dangerous rays is highest during periods of low solar activity when the sun's shield is weaker.
Which means for future astronauts traveling deep into space, away from Earth's protection.
Times of heightened solar activity, the very times when CMEs are more likely, might actually be the safest time to travel because the sun is providing a stronger buffer against the wider universe.
The star that defines our greatest risk here on Earth is simultaneously our first line of defense against the rest of the cosmos. A truly profound thought to end on.
It really is.
Thank you for joining us for the deep dive.